providing regulation. But what this chart shows, and this was the NREL study for the Eastern Interconnect, and they did a similar one for the Western Interconnect, and really the KEMA study is sort of the California study of integration of resources. And what this chart shows is the increase of regulation based on these scenarios. And this scenario 4, that's an error. That's actually 30% penetration. They jumped it up to 30 on that one. And basically it was the kitchen sink approach. So they looked at this blue line, which is load only, which is how much regulation are you buying right now. And so they looked around and, this is, about what the regulation is required in these different areas. And then as you go to a reference case of 6% wind renewable, you can see the jump in regulation needs across some of these control areas. And then what they said was, well, look, maybe some transmission can get built, maybe some can't, maybe we'll do a lot of offshore stuff, maybe not. And so they went through various scenarios, and then they did the kitchen sink approach. They said, how would that affect regulation in these various areas? And you can see the amount of regulation skyrocketed. They also very clearly said, we don't need storage for handling this. We just need a lot more regulation. Now, how that regulation occurs, we don't really know or really care in this study. But this, we do know we're going to need this much more regulation in order to bring in these, this penetration level. You have to couple this, and I don't think I have the chart on it. You have to couple this last one with the Carnegie Mellon study, which looks at using fossil plants for doing regulation and the concern on emissions, both for greenhouse gas and for criteria pollutants. And you can draw the line saying, well, look, there's really one good way to handle this regulation, at least to handle a good portion of it. So, we talk about regulation, from renewables, and so I'll just slide over to this chart. This is, this is looking at a microgrid on the island of Lanai. It's one of the first high penetration PVs. It's a 1.2 megawatt PV system put into about a 4 megawatt microgrid. Now this isn't the actual output of the PV array. I didn't have that data available. What this is it's the NREL snapshot of the solar radiation, global horizontal solar radiation, that you can infer what the output would be like. The only difference would be is this is taken from a single spot as opposed to 18 acres of solar power that they required in, 8 acres of power they needed in Lanai to cover the 1.2 megawatts. So it would be a little bit smoother. The blue line is just an indication of how a battery system could help smooth that out. So, and Sandia has been studying this quite a bit, and they're looking at this mass tripping of PV has to do with the voltage ripples and the fact that these inverters are all based on IEEE 1547 that specifies the trip points for under voltage. And so suddenly, you're creating a lot of power with PV, a cloud comes across, that power goes away, your generators are trying to respond. In the meantime, the voltage sags, and then the inverters, which are automatically set to trip, knock off the rest of the PV that could be on the line. Now there's work on adjusting that, and actually the Dutch was pretty far ahead. They have a high level of combined heat and power district heating and cooling, and initially they also set those systems with very tight protective settings, figuring that what they wanted to do was get them off the line in case there was a problem. And because the penetration level had gotten so high, when they dropped those units off the line, all it did was exacerbate that problem, and they had grid-wide trips. So, quick example, this is the island of Hawaii. This is one of their 2 major wind farms. This is just an example of several things. First of all, the light blue line is the raw power output from the wind farm. The light blue line using a 2-second rate of change is what a 4 megawatt storage system, fast acting storage system, can provide to smooth that out. This is over a 90-minute time frame. There's only 15 minutes of energy stored, but you can see the state of charge is you're able to maintain right around a 50% state of charge. What that's showing is that this regulation is very close to being energy neutral in the sense of going up or down, at least over this 90-minute time period for what you're looking for here. Some of the commercial demonstrations that we've done, I've mentioned several of them, the Office of Naval Research, ISE, Proterra, they both are, it's the 10-minute charge. You don't have to have your application shut down for a long period of time. You can recharge these batteries very quickly. And then the Megawatt Alti ESS, quick picture of the trailers, batteries set inside the trailers, commercial operation since over a year ago, and frequency regulation and then ramping response. Now, some of the commercial validation, these are the 2 trailers we delivered. You can actually see the individual cells in this case going through the battery systems. And really the only battery system right now, the advanced lithium ion, that's been used for frequency regulation. This is one day in the snapshot of a PJM doing their frequency regulation. This is, Dan, what they're asking for. Every 4 seconds, they're saying, look, we need you to discharge or charge or discharge or charge. And as you come across the period of time, this is how they're maintaining balance on the system. Once again, over this 24-hour period, you can see, once again, the state of charge is the blue line. And, roughly energy neutral signal over that 24-hour time period. So you don't need a lot of energy storage in order to provide this in this application. Yes, sir?
Yeah, that was just my question is, what's a rule of thumb for the amount that you need for regulation, say, in the context of solar versus wind versus something, else?
Yeah. So you ask a really good question, because I'm going to try and answer it in a few different ways. Typical large grid, California, macro grid, a lot of things tied together. For frequency regulation, they usually say 1 to 2%, 1.5%. So if you're out in California, you're at, I mentioned, a 30,000 megawatt load, you've got about 300 megawatts of regulation. So that's typical grid. It's just your load that's really varying. You start bringing in more renewables. Will the load grow in California? Let's say it goes to 40,000, but now you're at a third of that is renewable, right? 33% RPS, and they're saying during periods you'll need 4,000 instead of 300 or 400 megawatts. You're going to need 4,000. So going from 1% to 10%, right? So 10% at that point. When you get into So that's the macro grid, which is probably what you're interested in. When you go to the microgrids or remote grids like you'll see in the Hawaiian Islands or up in Alaska, you're going to see probably 10% frequency regulation at that point, 10% opportunity. What you saw on that one chart was about 25% for just smoothing that very erratic wind. But that's a pretty, that happens to be in a pretty erratic area of the island, and so it took a lot to help smooth that out. And that was a simulation, just for anybody know that. The wind data was accurate, and then the study we did with them was what does it look like for various levels of study.
Right. You said 30,000 megawatts, but I would assume that that's over, say, an hour's period. I'm wondering how much, there's kind of some terminology problems here, because 10% of 40,000 megawatts isn't exactly a storage unit. In other words, does that be?
It's power. It's power. 4,000 megawatts of power.
Yeah, but is it 4,000 megawatt hours worth?
No, it's power. It's power, and then what I've been trying to point out is that the frequency regulation is relatively energy neutral, so your hours of storage can be extremely short.
That's kind of the other parameter I was looking for. What's short? Half an hour? 15 minutes?
15 minutes. Actually, I'll say 15 minutes. And I'll tell you why, is that a lot of the regulation work that's being done at these ISOs, they are now looking at a 15-minute increment for doing their frequency regulation. So what they're looking for is something that can provide 15 minutes of regulation within that time period. So Beacon, ourselves, A123, their systems are designed around providing power for 15 minutes.
So I guess the big takeaway then, in a way, at least for somebody like me, is that if you can get 10% of the capacity and have it as for 15 minutes, then you've got it covered as far as introducing the renewables into the system. You're talking about 30% of renewables.
I don't know if I would take it that far, because at that point you're assuming I'm going to provide all the regulation for that 4,000 megawatts or so, 10%. And I think
Yeah.
some of that regulation is not going to be done just by storage. It's going to be provided by other generation, might have a longer time frame to it, something
Sure.
like that.
No, I'm just looking for kind of an envelope, an understanding of how big the parameter is. Is it as big as a bread box? Is it as big as a refrigerator?
So in California, they're talking roughly about a 4,000 megawatt opportunity for storage. You go once again to Dave Hawkins, who's been cited earlier. There's been comments from him about how much storage, how much storage is available, is required to provide this. And you can actually do some research on the internet, and you can come up with that quote.
And that technology is available right now, right?
Yeah,
Could be. It's just a matter of deploying it and building it.
correct.
Okay.
Correct. I've got 3 minutes, so this is a commercial. Actually, this is a very short commercial, but this is just kind of what it looks like in some of the specs. But I've actually got brochures outside that have better information than this. What it would look like if you built a bigger system. It's about 2 acres there. That's a 20 megawatt, which when you look at 20 megawatts, it's really 40 megawatts of storage, because you can absorb 20 or discharge 20. A couple of the value propositions, and I've been working with some of the rural co-ops that are out there, and what they look at is, if I'm in an unbundled, when they say unbundled ancillary service area, it means you can participate in a market. Now, every hour there's a price for doing regulation. So, they right now just pay on a yearly basis, they just pay this, but they could actually shift it to a self-supply. Instead of having an uncontrolled variable expense, it would be known. But this is the real key takeaway, and this is a good key takeaway for across the system. You put these in, and you can put these in anywhere on a distribution line, at a customer site, behind their meter. Behind the meter gets a little difficult because of just meter charges, but on a distribution line. And now not only are you doing frequency regulation, but you can now provide voltage support. And I live in California, I do work at the PUC, get involved in some of the high penetration RPS stuff. And I see this as a way, right now, PG&E, San Diego Gas and Electric, SCE, they're all paying money to ISO for the regulation, which all shows up in our rates. There's no reason why they couldn't own this system, put it on their distribution lines, self-perform their regulation, pay for the system, and now have the very cornerstone of the smart grid. Self-healing, available to put a system on the distribution line to do voltage support for their customers on the distribution line that they're typically holding to a 15% penetration level, and now have voltage support. And that's a key feature. I think there's some great opportunities for that here in California. With that, it is the long cycle life and fast recharge that allows these to be cost effective. That's it. Yes, sir.
So do you see yourself going to back to light duty vehicles?